Okay, I'm gonna attempt to solve this problem using Prim's minimum spanning tree. So this will be an explanation of Prim's minimum spanning tree. I have already made a video on Kruskal's minimum spanning tree, and I have achieved a time complexity of O of n square log n and a space complexity of O of n square with Kruskal's minimum spanning tree. So I'm gonna do the same time complexity and space complexity with prims first and then optimize it such that the time complexity will be reduced to O of n square and space complexity will be reduced to O of n. Okay, so this is what I'm gonna achieve with prim's minimum spanning tree right now. So let's go with the uh, basic prim's minimum spanning tree algorithm first and then optimize it. Okay. So uh, this is the problem. The problem is we have a set of points and the distance between each point is the Manhattan distance between them. So the Manhattan distance is the difference of x coordinates plus the difference of y coordinates, absolute value of the difference, right? And so we'll have to return the minimum cost to make all points connected. So we'll be using Prim's minimum spanning tree for this. So let's go with that. Okay. So first of all, what we do is we identify an adjacent list for each of this, right? So let us identify these points as with the indices 0, 1, 2, 3, and 4. Okay. So I have pre-computed all the Manhattan distances, and these are they. Okay. So let us choose a point here. By default, let us always choose the 0th point. Okay. So 0th vertex 1, 2, 3, and 4 here. Okay. Let us choose a 0 by default. Okay. So we've chosen 0 here. So the adjacent list would be this. Okay. It would be this. Okay. 0 to 1 is 4 and 0 to 2 is 13, 0 to 3 is 7 and 0 to 4 is 7. Okay. So I'm gonna put all of these into a heap. Okay. So right now the heap will contain, so I'm gonna have a heap and the heap is going to contain 0 to 1 which is 4 and 0 to 2 which is 13, 0 to 3 which is 7 and 0 to 4 which is 7. Okay, so in the heap this is a minimum heap. Okay, min heap. So obviously this will be the top item over there, right? So when we poll the heap element, this is what we're going to get. Okay, which means that we can make a connection between 0 and 1, and the uh, the distance would be 4. Okay, the cost of connecting would be 4. Cost of connecting is the Manhattan distance, which will be 4 here. Okay, so we can connect 0 to 1 here. Now what we'll do is uh, we'll add all of these as well in the heap. Okay, so earlier it was 4. Now this is removed, right? So we have this and this here, and the min heap will obviously give 3 here. So we'll make a connection between 1 and 3 and the cost would be 3, right? So the solution will be 4 plus 3 so far. Okay, and now because 3 is the current item, what would we do is we are going to add all the items that all the adjacent list that contains 3. So these are the two items that contains 3. Okay, 3 here and 3 here. Okay, so all the others are already present. So right now this 3 is also eliminated. So the least we have here is 4 here. Okay, by looking at this, so the heap min heap would do that for us, and the least we have here is 4. Okay, so we'll add this and it would be 4. Okay, So the solution would be plus 4. Okay, and then we have connected 4 of them now. We have only one left. So we have to add this last item as well because 4 is present here. The current item we are at is 4. The current vertex we are at is 4. So we'll have to add that as well. So the min heap right now would be 7. Okay, but then uh, so if we check, so we'll actually have to maintain a visited set here, and if we maintain a visited set, the first one was 0, and then we have visited 1, and then we have visited 3, and then we have visited 4, right? So this must have been added because of 3 and 0, so both of them are present in the visited set, so there's no use of adding that, right? And then the next one would also be 7, so this is also removed, this is also removed because 0 and 4 both are present in the visited set. Okay, and then uh, this 7, this is also present in the visited set because 1 and 4 are present in the visited set, right? And then we get to this one, which is 0 to 2, sorry, 1 to 2, and the distance is 9. Okay, so we'll have to connect 1 and 2, and the Manhattan distance is 9, so that would be our solution. And then we have visited all the nodes here, and we can exit this problem, and the solution would be 20. Okay, so this the time complexity for this one, so to actually generate uh, this will take O of n square time complexity because there are n vertices, there will be n about n square edges. Okay, so each vertex will be connected to every other vertex except for the current one, right? So that's the reason we'll have O of n square here, and then we are applying a heap on top of that, and we are trying to get all the elements over here. So um, we'll have to, like, we have visited almost like 1 2 3 4 5 6 7, so we have visited almost all of these here, so we are not reducing it to exactly um, these items, the unvisited items here, so that would make it similar to a heap sort. So that would mean that the time complexity for that would be O of mm, n square log n square, which is equivalent to O of n square log n. Okay, so I've gone a little fast paced with this because I'm actually going to optimize this a little so that we can achieve. So the space complexity here is also O of n square because we have to store this adjacent list, right? So without storing this and without having to go through this time complexity and space complexity, I'm going to reduce the time complexity and space complexity to O of n square and space complexity to O of n. Okay, so that's the reason I have gone a little fast paced with this one, and the program for the current O of n square log n algorithm, Prim's MST, Prim's minimum spanning tree algorithm with O of n square log n is present here. Okay, so this is the algorithm. I'm not going to write it again. So now I'm going to optimize this one. Okay, so I'll first erase this, and then I'm going to explain what I'm going to do to optimize this one so that we can achieve the uh, time complexity and space complexity we've just discussed. Okay, so uh, okay, these are going to be 0 1 2 3 4. So what we are going to do right now is we are going to maintain an array. uh, so we have 0 1 2 3 4. These are the vertices we have, right? So let us make all of them as infinity. Okay, so this is the minimum distance array. Okay, minimum distance array. I'm going to make all of them a infinity except for the first one, because the distance from 0 to 0 will be 0. So I've just done it initially, or I can actually make it infinity as well. It wouldn't matter a lot. Okay, so similar to the earlier Prim's minimum spanning tree algorithm, this is just a uh, optimization of that. So we are going to choose 0 here. Okay, so now because we have chosen 0 here, we'll have to calculate the uh, Manhattan distance from 0 to every other node. Okay, so what we are going to do is we are going to have a visited indices set. Okay, in this set initially it will be empty. So once we've chosen 0, we're going to add it. Okay, 0 is added to the visited set. So except for 0 to 0, everything else will be computed here. Okay, so right now, because we have calculated that the distance between 0 to 1 is 4, and we are calculating from 0, so 2 will be 1, right? So at index 1, we have that the distance is infinity, right? So we are going to reduce this to whatever we've computed so far: 4, 13, 7, and 7. Okay, so 4, 13, 7, and 7. Okay, okay, so this is what we've computed so far. So in all these, okay, which are not presented in visited set, so we are going to simply iterate through this minimum distance array, and we are going to check for each element. If it is not in visited set, then and only then we are going to calculate this. So the minimum here will be 4. Okay, 4 is the minimum. So we are going to catch this one index here, and then that will be our next element that we are going to visit. Okay, so which means that we have made a fixed connection between 0 and 1, and the distance here is 4. So we are going to add this to the solution. So solution will be 4. Okay, uh, because 1 is the least distance here, right now we are going to compute with 1. Okay, so now that 1 is here, what we're going to do is we're going to compute the distances from 1 uh, to the other elements. Okay, we're going to compute this, and this. Okay, so we have started from 1, so this is a 2, and from 1 to 2, the distance we have computed so far is 13, and now we have computed it to be 9. Okay, so the distance from 13 will be reduced to 9. Okay, so we have eliminated this one, and this is not necessary right now. So the distance from 1 to 9, 1 to 2 is 9. Earlier it was 13. 9 is less than 13, so we are going to change it to 9. Okay, and the distance from 1 to 3 is 3. Earlier it was 7, so we are going to reduce it to 3. Okay, we have reduced this to 3, and then right now we are at 1, right? So we are going to compute this, and this. Whatever is the minimum, we are going to catch that. Okay, this is the minimum. 3 is the minimum. Okay, so because 3 is the minimum, we are going to get the index 3. Okay, 3 will be our next iteration. Okay, so 3 is the next iteration here. So we are going to visit 3, and because we have visited 3, it means that we have made a fixed connection between 1 and 3. Okay, and the distance is 3. Okay, and then right now we are at 3, right? So because we are at 3, we are going to add these both, 2 to 3 and 3 to 4. Okay, so 2 to 3, so right now we are computing for 2, because we are coming from 3, we are computing for 2, and whatever we've got is 10. 10 is actually greater than 9, so we are going to not make any changes. and then 3 to 4 is 4. Okay, so earlier for 4 we had 7 is the minimum distance, and right now we have it as 4. Okay, so the minimum distance from 7 will be reduced to 4 here. Okay, it is reduced to 4 right now, and we have uh, 0, 1 and 3 in the visited set. So among the remaining, the minimum is 4. Okay, this is the minimum, and we are going to catch the next index. Okay, so right now we have computed, so the solution, I forgot to add this one, 4 plus 3, which we've made here, and then we are going to visit 4 here. Okay, so 4 is being visited. Because we have visited 4, uh, the Manhattan distance from 3 to 4 is 4, so we're going to add that here. Okay, and then uh, so 4 is also visited right now. So what we're going to do is we are going to, okay, these are all visited here, so we are going to calculate the minimum in the minimum distance array, which is not present in the visited set. Okay, and this is the only item that is not present in the visited set, so obviously that will be the minimum, and 2 is the one that we are going to visit next. Okay, so we are going to visit 2, and for 2 the minimum distance is 9, and that is from 1. So we have made note of that here, but that doesn't really matter in our current problem. So from 1 to this is the minimum distance of 9, and that will be added here. Okay, so the solution would be 20 again. Okay, 4 plus 3 plus 4 plus 9 is 20 again. So I'm going to attempt to solve this in Leetcode right now uh, by writing a program. Okay. Okay, so first of all, I'll just identify the length of this into n. Okay, uh, so I'll add a visited set, and there's nothing present in this, and then I'll add a array for minimum distance. Okay, okay, so for this what I'm going to do is from I is equal to 1 instead of 0, I less than n I plus plus. It doesn't matter if I do it with 0 or 1, I'm just going to start with 0, so it doesn't really matter here. Okay, so I've initialized it to the max value, and now I'm going to take a queue because it makes it a little easier. Uh, okay, so I'm going to start with 0. Okay, start with 0 while queue is not empty. I'll have to continue through this. Okay, so what I'll have to do here is I'll have to calculate the Manhattan distance from this point to every other point, right? So for that, I'll have to use a for loop. But before that, I'll have to capture whatever is present here. I'll capture it in a temporary variable, and this will right now have 0, right? So I'll first add it to the visited set. Visited indices dot add current. I'll add it to the visited set, and for int I is equal to 0, I less than n, I plus plus. So for all the other items, what I'm going to do is I'm going to capture the minimum distance of I is equal to math dot, okay, I'll expand this a little, math dot minimum of minimum distance of I, so the current minimum distance and whatever we're going to compute right now. So that will be the Manhattan distance between the points at I and the points at the current position, right? So I'll have to implement this Manhattan distance. Let me do that first. Math dot absolute value of x, x1 minus x2 plus math dot absolute value of a of 1 minus b of 1. Okay. So this will give me the Manhattan distance. So I'm going to calculate the Manhattan distance, and if whatever is the minimum will be stored in this, right? So I'll have to have a variable to identify the minimum distance so far. Okay. Uh, okay. So the minimum distance, let me initialize it to integer dot max value. Okay. And then next index that we're going to choose, let us initialize it to current index. Okay. And then if the minimum distance, if the current minimum distance that we've identified is less than the minimum distance we have so far, what we'll do is we'll store the minimum distance into this minimum distance, and we'll identify that as the next index. Before this, I'll first have to identify if this is not already visited. Okay, visited indices dot contains I, then simply continue, don't do anything. Okay, so in this case we'll get the next index. So we have initialized the next index to be the current index. So if next index is equal to the current index, it means that nothing has happened, so we'll have to return the solution. Okay, I forgot to actually add the solution. Solution is equal to 0. Okay, and if this is not the case, what we'll have to do is we'll have to, first of all, what we have to do is whenever we visit this, right, we'll have to increment the solution by the minimum distance of the current position. Okay, we'll have to do this, and next will be identified here. I think that should be enough. Okay, forgot to add a minimum return statement. Okay, why has this happened? I've started with 0. Okay, I actually forgot to add the next pointer to the queue. Okay, so queue dot add next index. That's it. Okay, so I'll try to submit this. Okay, it is better than 86.81%, which means it is about the best solution we can obtain with. And you can see that the earlier ones are 1886 milliseconds here and 2125 milliseconds here, which means that it is O of n square log n. And right now we are doing it with O of n square time complexity. So let me explain how exactly it is O of n square time complexity here. So what we're doing here is we are doing this exactly for O of n times, and we are calculating the minimum over here, which means this for loop, and this is also O of n time complexity. So of O of n into O of n will be O of n square, and then we are making use of this space, which is O of n, and this space, which is also O of n. So of n plus O of n is again O of n. Okay, so the time complexity for this one is O of n square, and the space complexity is O of n. Okay, so that's it for this problem. Thanks for